Hi folks, we're now going to take a look at number 2 from the related rate sheet. So here, let's read the question. We've got a police cruiser is approaching a right-angled intersection from the north, is chasing a speeding car that has turned the corner and is now moving east. Okay, when the cruiser is 0.6 kilometers north of the intersection, the car is 0.8 kilometers east. The police determine the distance between them, and the car is increasing at 40 kilometers an hour. Okay, so they tell us if the police cruiser is moving at 80 kilometers an hour at that moment, what is the speed of the car? Okay, so what we have to do is, again, a diagram here I think is essential. So let's let this point here represent the intersection. Okay, so you have the police cruiser that's coming down from the north. Okay, and you've got the speeding car which just turned the corner and is moving east. Okay, now what we're looking for is the speed of this car, and what they give us is the speed of the police cruiser and the speed of the distance between them. Okay, so the first thing I'll do here is I'll draw a line representing the distance between them at some time. Okay, and I'll call that capital D. Okay, so we have to somehow find a relationship between this distance between the cars and the information. The other information that I'm given is how the police cruiser is moving, and I'm looking to determine the rate of change of the speeding car. Okay, so here again, look at the geometry, and it seems as though working with this right angle triangle. Okay, they were very clear in telling us that the intersection is right angled. Okay, so it looks like we're going to be working with this right angle triangle, and since we're looking for or have information relating to these distances, looks like Pythagoras is going to be the way to go. Okay, so I'll call this distance P, okay, for the police cruiser, and I'll call this distance here S for the speeding car. Okay, now the information they give us is they give us the rate of change of the distance between them with respect to time. Okay, and that's 40. Okay, they give us the rate of change of the police cruiser. Okay, now this police cruiser is moving towards the intersection. So this distance that we're actually working with, which we're calling P, oh, sorry, let me move my hand out of the way. This distance that we're calling P is actually decreasing as time goes on because it's getting closer to the intersection. So we do have dP dt, okay? But that's going to be a negative rate of change. So it's 80 kilometers per hour, that's the speed. But when we look at the velocity, when we think of the fact that this distance is actually decreasing, it makes sense to be using a negative value. Okay, because we know that a negative derivative corresponds to a decreasing value. Okay, and what we're looking to find is ds dt. So this is what we're trying to determine. Okay, so again, let's go back to what we have is we have a right angle triangle, and when we're looking at a right angle triangle and we want to use Pythagoras, we have to use the side lengths. Okay, so the relationship that we're going to be using is d squared equals p squared plus s squared. Okay, and since we're looking for and have information about the rates of change, I'm going to do what I've done earlier, and I'm going to take the derivative with respect to t of both sides. Okay, I don't bother isolating the variable because implicit differentiation will be a lot easier than having to work with square roots. Okay, so I'm going to take the derivative with respect to t of both sides. Okay, and now I'm going to apply the chain rule to solve this. So again, I'm not going to write it all out like I did in the previous example, but here, if I'm taking the derivative of d squared with respect to t, first I take the derivative of d squared with respect to capital D, so 2d, and then the derivative of d with respect to t. Okay, and same thing here, since this is just a sum, I can split it up into the sum of the derivatives. So again, first I take the derivative of p squared with respect to p, 2p, and then the derivative of p with respect to t. Okay, and lastly, this will be 2s ds dt. Okay, So let's look at the information that we have. We have how the distance between them is changing. We have the velocity of the police cruiser. Okay. We know P and S at the particular moment in time that we're interested in. Okay. This is 0.6 and 0.8. Now the only thing we're missing here is the distance between them at that particular moment. So again, you'll notice in my diagram, I did not put any numbers that related to variables which, well, quantities that were variable. Okay, so I'm going to draw a separate little diagram here. Okay, so at the moment we're interested in, the police cruiser is 0.6 kilometers away. The speeding car is 0.8 kilometers away, and we want to measure this distance here. Okay, so just use Pythagoras. D is equal to the square root of 0.6 squared plus 0.8 squared. Okay, you might already notice this as being one of our nice triples. Okay, and if you calculate that, you'll get 1. Okay, so now let's input all the information, and we'll see that the only quantity remaining is that rate of change we were looking for. So we have 2 times 1, and the derivative of d with respect to t is 40. Okay, equals 2 times 0.6, and this velocity here was negative 80, plus 2 times, well, we know that this is 0.8, and ds dt ends up being our only unknown left, which is exactly what we're looking for. So let's solve for ds dt. Okay, and again, as long as you're very careful in putting this into the calculator, you don't have to write a whole bunch of steps. Okay, so let's start with the left-hand side. So 2 times 40 is 80. Okay, divided by, before we divide, let's start over. 80, and here, well, we're going to bring this to the other side. Since it's a negative, it'll become an addition. So 80 plus 2 times 0.6 times 80. Okay, and now we have to divide the coefficient of ds dt. So divided by, please make sure you put this in brackets, 2 times 0.8. Okay, and there we have our rate of change is 110 kilometers per hour. Okay, and again, this is certainly a way that that policemen can determine the speed. Okay, because what they can measure, so they can measure their own speed. They can measure the speed at which the distance between the car and itself is changing, and then using that information, you can calculate the actual speed of the car. Okay, so again, this idea of related rates, that I use some other known rate to determine the rate of change of another quantity. Okay, that's it for this one.